Hello and welcome to the Joint Inspection Team's Level 2 training course. This training course will cover high-rise residential block inspection and a HHSRS assessment. My name is Richard Chubb, and to introduce you to the team who will be on the call today, I'm Richard Chubb and I'm Principal at EHO in the Joint Inspection Team.
My name's Paul Stevens. I'm the Principal Building Control Surveyor for the Joint Inspection Team.
And I'm Jonathan Herrick, Principal Fire Engineer for the Joint Inspection Team.
That's great. Okay, and I'm just going to ask my colleagues now to turn our cameras off so that everyone can concentrate on what's being said. Okay. So the format of the training today, we have an online training course which is going to be delivered in two parts. The first part is a pre-course familiarisation with the building, after which you will undertake an HHSRS assessment of your own. The second part of the training course will be attendance at a live online training event during which we will discuss how the team has rated the relevant matters and has scored the HHSRS hazard, and a talk through how we will create an appropriate notice, including the phrasing of any associated schedule. The aims of the course of part one, which is the pre-course familiarisation. This presentation covers an inspection of a hypothetical high-rise residential building. Our commentary aims to explain what we observe and any impact on the building safety. You should take note of the presentation and undertake your own HHSRS scoring ahead of the training day. Remember to score the relevant matters, which are scored 0 to 3, with 0 being not of concern and 3 being of extreme concern. You'll then need to obviously assess the likelihood and also the harm outcomes. It should take between 2 and 4 hours for you to watch this presentation, read the associated documents and make your HHSRS assessment. Whether you work in groups or alone, you'll get more out of the part 2 training if you have engaged fully in part 1. You will note that we have provided a fire risk assessment and a fire strategy with the join-in documents to go with this video. You'll note that some of the information in the strategy is not consistent with what is on the diagrams. This is on purpose and it is what you will see in real life. So don't worry if it doesn't exactly match up. Okay, moving on. So part one, the building inspection, what we know before the inspection. So presume that we have served a section 235 notice and requiring the production of a lot of different documents. This is the first part of the presentation will cover what we have received prior to going on the inspection. Okay, over to John.
We've learned that the building was completed in 2012, that it contains 64 flats or studio apartments. The principal construction was steel frame with concrete floors between levels. There's also a concrete stair core that is shown on this schematic on the left-hand side of the diagram. Floors 1 through to 8 have an identical floor plan layout, and they're shown on this diagram as a box covering a number of floors marked leaseholder flats. There's a 15-metre travel distance from the furthest flat entrance door to the staircase lobby. And there is a smoke extraction system, which is shown as the smoke shaft on this diagram, and an AOV, that's an automatic opening vent at the head of the staircase. The diagram also shows us that there is basement car parking, that the ground floor accommodation is occupied by 2 commercial premises and an unstaffed reception area. The front door, the main access into the building, is secured with a key fob access, which is designed to secure against any unauthorized access into the building. That the height from the ground floor to the highest occupied floor is 26 meters, and that there is a separate exit from the basement car park to the outside. For the purpose of the HHSRS scoring, the building's clearly post 1979. Now, this is a typical floor plan layout for floors 1 to 7. Now, the previous slide said that 1 to 8 are identical. While that's true, the cladding on the building at different floor levels, differs at floor levels. So on floor 8, you will see that the wall system is different. So let's start with the wall system. And on floors 1 to 7, you will see that the predominant wall system here is between terracotta, which is the green lines, which are the end caps, if you like, to the building, and ACM, which is between the balconies here, and hopefully you can see that being pointed out. It's a coloured grey. The black lines on the building here, these are balconies that serve each of the flats for outdoor space. Now, moving on to the floor plan itself, to the left-hand side, you can see the staircase enclosure. You can see that the door from the staircase there opens towards the staircase, and so that's in the direction of travel. If you were escaping a fire in a flat and heading into the staircase, those doors open in the direction of your travel. As we come out of the staircase enclosure, you can see that there's a lift, and directly opposite the lift are 2 service shafts. There's also a dry rising main outlet and a lobby door before we get onto the residential corridor itself. Now, the dry riser is effectively just a pipe that runs from the ground floor and then has an outlet on every upper floor, and it's charged with water by the fire service when they arrive, and that delivers the water to the upper floor so that they don't have to run hoses up the staircase enclosure. You'll notice that it's a dry rising main, which implies that there isn't normally any water in that pipe at all. A wet rising main would be required in buildings that are over 50 metres tall, because fire service pumps can't pump as high as 50 metres on a constant basis. And that would be permanently charged with water and would have some pumps to get the water to the higher levels. Now, you'll see at the end of the residential corridor that there is a smoke shaft, which has a smoke extraction system, and that's designed to take smoke from the residential corridors that might get out of a flat that's on fire, maybe come out through the front door, get into the residential corridors, and that system is designed to draw that smoke out of the residential corridor and discharge it at roof level. Now, ideally, we would expect to see some inlet air if we are drawing air out of the corridor. We would expect to see some kind of inlet air so that fresh air can replace it. Otherwise, we create something of a vacuum. That is not showing on these plans, and we'll look at that in particular when we get to the building and do the inspection itself. As for the location of the ACM cladding, going back to the cladding, you'll notice that that's adjacent to the balconies and connects to the inside face of each of the flats. So now we look at floor 8, you will see that the actual floor plan layout is just the same as the floors below, but our cladding system has changed on this one. We'd say that this is the crown of the building, and it's this yellow colour, and that denotes in this case an HPL wall covering, which is a high pressure laminate wall covering cladding system to the outside of the building on this floor. So that's dealt with the residential floors on floors 1 through to 8. As we descend now to the ground floor plan, you will see that the ground floor has that fob access control to the front door. And then immediately in front is a reception desk with post boxes and a small office for the occasional staff that work in the building. You can see that it's necessary to walk past the entrance to the staircase in order to get to the lifts that service the building, and that there's no communication at all from that residential access point to the commercial buildings, commercial 1 and commercial 2, as shown on this plan. The bin store is accessed from the outside through a separate door and does not communicate at all with the inside space. You'll also see a ramp marked there, which is the vehicle ramp, which leads down to the basement car parking areas. So down onto the basement areas, we can see here that as we come out of the staircase enclosure, there is the lift adjacent to it, that there's a door that goes straight through to the car parking and cycle store, and that takes up most of the basement area, but there is a small room accessed from the car park, which is the plant room for the building. At the far end of the basement car park, there's an alternative exit route and another small staircase, which goes to the ground floor and to fresh air.
Okay, so then we look at what's inside the flats regarding the services to the block and to the flats themselves. We have hot water and heating provided by a gas boiler that serves the radiators to each flat, and there's gas pipes actually come through the service riser in the firefighting lift. And the difference between a firefighter lift and stairs to a normal access stairs is a firefighting stairs is required above 18 meters. In this case, that has been provided. We have gas service risers coming up through that area that then go through the ceiling voids to serve each gas boiler to each flat. There's a gas boiler to the common areas contained in the plant room of the car park. Drinking water is provided via pumps from the central water tank in the basement plant room. There's electric meters for each flat, and they're contained in cupboards to the protected corridor. And also there's a secondary electric supply for use for the lift should power fail, and for the smoke extraction system. And the secondary electric supply can come through via a different transformer, surface wire, or it could also be provided via a secondary backup generator in case there's a fire and there's a total power failure to the building, and where you need systems to work for life safety.
Okay, so provided with the joining instructions to the presentation, you should have been provided with a fire strategy document, which was produced at the planning stage and may not be as built. You'll also be provided, you have been provided with a fire risk assessment, or at least a summary of the fire risk assessment, as quite often they're about 60-70 pages long. So at this point, it's best to pause the actual presentation and have a read through these documents, as you'll need to read them prior to doing the inspection itself. So if you want to pause or stop the presentation now and read through them and then restart this after you've actually read through them. Okay, do that now. I will continue with the presentation now. Okay, over to Paul.
Okay, so as you know from the floor plans, you can see what type of cladding is on the building, and we do have phenolic foam insulation. So in this case, we need to look at percentages. So we have ACM, which is 20%, and it's category 2. So that means the ACM does contain some fire retardant to that product. However, we'll talk about a bit later on how that works with the insulation behind. We have 20% HPL, which is Class D, Euro Class D. We'll talk about the classification system in a little bit further. And there's no valid BR135 report for the wall system. We have 40% terracotta rain screen with a BR135 pass for the wall system. We have 20% glazing. And when we talk about BR135, that is an assessment of the British Standard 8414 test undertaken by a competent engineer to look at the parameters that are set for the test and to establish if the BR135 is classification is a pass, not just for the cladding system, but also looks at the fixings as well. So we do have phenolic insulation behind the ACM, and that does have an effect on the category of that system. It does make it worse, which we'll talk about in the next couple of slides. So we'll talk about categories. We have category 1, category 2, and category 3. As you go down the scale, category 3 is the worst type of ACM. It has no flame retardant properties to that material, and that's why, as you can see, the values megajoules per kilogram increases per category, where category 1, the material of limited combustibility, it's very low. And again, this is a product only. If you look at the insulation behind it, the system itself does become worse. And when we look at that in the next couple of slides regarding if it was some sort of stone wall insulation instead of a phenolic foam, rigid foam insulation type. So this is the classification system. A1 is the best type of system. In this case, on the top crown of the building, we do have HPL, which is classification D. As you can see where that belongs onto the table. So the scale goes, so we look at the product classification, and it goes from A1 to F, and you can see the definition where it's considered to be non-combustible and limited combustibility, and how it contributes to the fire. So the HPL is class D, S2, D0. So we look at the classes, what that represents. The classes of reaction to a fire performance, A2, B, C, D, and E, are accompanied by additional classification related to the product of smoke. So that's where the S comes from. So that'd be on a scale of S1, S2, S3. As you go further down the scale, the worse it becomes, with S1 indicating the lowest production and or flaming droplets, particles, and that's the D classification, where D0, D1, D2, with D0 indicating the lowest production. Note, when a classification includes S3, D2, this means there is no limit set for the smoke production and for the flame droplets or particles. Difference between classification 1, 2, and 3 is basically the calorific value of the actual ACM, which is undertaken by additional tests, also known as the bomb test.
This slide shows us the government's consolidated advice note and is a table that represents the testing that MHCLG has had done and how various types of ACM with associated insulation have fared in those tests. So down the left-hand side, you can see that the type of ACM ranging from category 3 with an unmodified polyethylene filler. So this is ACM material with a filler of unmodified polyethylene. Category 2 is an ACM material with a fire retardant polyethylene filler. So this is like a sandwich with aluminium on two sides with that filler in between. And the best case is a limited combustibility filler between those two sheets of aluminium, and that's a category 1. Across the top, you can see the various types of foam insulation that have been used in association with these tests. And they include PIR foam, phenolic foam, and stone wool, where stone wool would be the best case in most cases. You can see from this test that the category 3 ACM fails with PIR foam and fails even with stone wool. This is the most reactive ACM material that you might find on a building. What we have on our building is a category 2 ACM in conjunction with a phenolic foam report, foam insulation. And the tests done by MHCLG showed that that test failed. And it's possible to access the reports, I believe, by clicking on those links. If they don't work, it's easy enough to find by looking for the MHCLG consolidated advice.
Okay, so as part of your section 235 notice, you've received a highlight report of what is present in the cladding system. So this has been provided by an external contractor who's been employed by the freeholder to give an opinion on what is present behind the rain screen and what the actual rain screen comprises. So it's a ventilated rain screen cladding system, as opposed to one that has just been bonded straight onto the external makeup of the building. The ACM is category 2, as we've stated previously, and you've been provided with reassurance via a BRE test certificate, which has been which has confirmed that it's a flat riveted panel and has all the category 2 characteristics. The HPL, of which there's 20% on the building, is Euroclass D S2 D0. So that means that it's combustible and produces a fair amount of smoke, but no droplets. The glazing tends to be non-combustible. 20% of the building is covered in that. There's insulation, which is a foil-backed phenolic foam. This has a Euroclass C S1 D0, so there's no dripping associated with it, but there is a limited amount of smoke which comes from it, so it is combustible. It's also not been taped at the seams of the insulation and is falling away into the cavity due to a number of missing or inadequate insulation fixings. There is cavity barriers. The horizontals are not attached to the sheathing board, which we'll come on to in a minute. They're attached to the insulation only, so fire could actually move around these barriers, and the vertical cavity barriers are missing. There's no disrepair of note to the outer surfaces of the cladding system. If we weren't provided with a cladding report, we would have to assume the worst. So just for your own sort of benefit there. Okay, over to Paul.
Okay, so when you go to the information gathering stage, you may get some details of the cladding system, probably build control drawings, sectional drawings, maybe some drawings associated with the planning permission. But technically, this is a horizontal cut through of the cladding system. This is where we have the ACM, and then there's a cavity, a clear cavity. There is a cavity barrier in place. We'll talk about it in a second. That's based on the fixed to the insulation. And then you have the sheathing board that provides bracing to the warning system, covered by a breathable membrane. And then you have the internal plasterboard to the flats. So the issue with this diagram here is we do have a clear cavity where the cavity barrier is in situ, is incorrectly fixed. It really should be fixed to the sheathing board, to a hard structure as to manufacturer's instructions. Is the insulation called to light, the insulation will then spread behind the cavity barrier. And then we've also got to think about the clear cavity. Sometimes in certain cladding systems, you do need a clear cavity set up by the manufacturers of that cladding system, but there's ways of dealing with it. In this case, an intermittent fire stop is part of the cavity closure. That's to help prevent when you do get a clear cavity and there's a fire or smouldering fire that's got into the cavity, it could be intensified by what's called the chimney effect, where oxygen is drawn in and pushed up with the fire, and that can intensify and spread the fire further up the cladding system. So it can bypass all the compartment stopping and any other sort of fire. If there was no fire barriers, it'd just be an open shaft for fire spreading. But in this case, there is an intermittent fire stop fitted to the cavity barrier. So when that does reach a certain temperature, that will expand and seal off that cavity. That will stop any fire spreading past that point. However, it's the fact that the cavity barrier isn't actually fixed correctly, and it's fixed to the phonemic foam instead.
Okay, so that is a brief summary of the information that we've received prior to an inspection. And now we are going to go through the on-site building inspection, which we will start, and as we always do, with an external inspection of the building. So over to Paul.
So when we first do an inspection, you need to get a feel for the building. In this case, we do have dimensions provided to us. From the previous slides, you're aware of the height of the building. You're aware of the internal corridor dimensions. The external dimensions are 30 meters by 20 meters. You've got balconies in series. So there was a balcony fire. Potentially that could cause a chimney effect as well, catching the next balcony or light. If there's not adequate fire stopping around windows and doors, if there was an internal flat fire, they can also then reach up to the balcony above. So it is a building above 18 meters. So you are following certain regulations set out by building control. It's slightly different if you do have a building below 18 meters. And as you can see from the color coordinated diagram, you have HPL, I spoke about, at the crown on the top story. So the balconies are also next to the ACM. So there was a balcony fire that can also then spread quite easily to the ACM itself. The other side elevation is also identical to the middle elevation. And as we spoke about, the 26-meter height measured from the floor to the top, from the ground level to the top floor level. So when we're measuring a building and it's above 18 meters, then we need to look at where we take that measurement from. And it's always the lowest ground level to the top floor level. And there's also access to the car park. So the car park does have security shutters, and so does the exit. That's to prevent any unauthorized access as well. So when we talk about the ACM, so we are aware that what materials are on the building. So then we need to sort of look a bit closely at what materials are presented to us. So normally we see the ACM laid out as a rivet flat panel system or a cassette system. The cassette system, technically through other research, has been deemed to be slightly worse than the rivet panel system. Sometimes the ACM is actually hard to identify. This is why you need to look at any external edges you can see. And the ACM is fitted to a steel frame system that gets fixed to the structure, and that provides basically the grid system, so the panels are easily attached. And the harder central core is attacked of the ACM is attacked by the fire. The aluminium starts to delaminate, and that spreads the fire further. So as we look around the building, we're also looking at any penetrations there are. As you can see, it seems to be a vent coming out through the cladding system. If there was an internal flat fire, this is a route where the fire could escape the flat and reach the cladding system. This could also be the same for any boiler flues that go through the wall as well. What we normally expect is a non-combustible ducting, or you could have an intermittent grill. Otherwise, you could be looking at other sort of fire stopping products on the market to prevent any fire escaping that flat and reaching the cavity system. So not just the vents, you'd be looking at other items as well, such as trickle vents to windows and doors that could also have an effect.
Among our other observations from our external view of the building, we consider firefighter access. Now, typically for a building of this size and height, we would expect access to 50% of the building as a minimum, but in this case, we had 100% access to the perimeter of the building, which is very good. The dry rising main inlet valve, which is where the fire service will attach their hose to charge the dry rising main pipe, was covered by foliage that had overgrown around it. So it was very difficult to see the location of the inlet, and we had to look very closely to find it. The fire hydrants were in the street, and in this particular case were approximately 100 meters away from the dry rising main. Now, as part of building regulations, that distance should be no greater than 90 meters. So we were just over what should be in place. So what that means is that it would take longer for the fire service to lay their hoses out from the hydrant to the point at which they can charge the dry rising main. There were no buildings close to this one that would cause us concern, for example, with fire spread from one building to another or from this building to another. So that was not a consideration or an issue in this particular case. And the building was protected with closed circuit television, which was there for security purposes. Our final exit route moving around the building took us to a gate that was adjacent to the car park ramp. It was also secured against unauthorized entry and was held in particular by an electric operated magnetic holding device. It was a self-closing gate so that it could not be left in the open position. It could be opened from the inside by using a green mushroom button. So strike the button, it disengages the magnet and the gate can be opened. But in case of power failure or emergency, there was also a green break glass cover override, and that's located on the wall to the left of this picture, just out of shot of the photograph.
Okay, so we've covered the outside of the building now. Now our inspection will move to the inside of the building, and what we do on site is that we tend to walk up the protected escape route to the top of the building, where we then restart our inspection. Okay, so what do we have here then, John? I see that we've got some form of opening vent at the top of the stairs.
Yeah, so here we are at the top of the staircase enclosure, and what we have is an automatic opening vent. We call it an AOV. That's that big plate thing that shows at the top of the picture. It's on a powered arm, and that is designed to power to the open position in the event of fire, which is detected by the smoke detector that you can see in the picture. That detector is part of an L5 fire alarm system, Now, an L5 just indicates that smoke detection is provided to certain positions or locations of the building only. Now, in a residential building, we don't expect to find fire alarm sounders throughout the building. That would be unusual in terms of the fire alarm standard. In a residential setting, these detectors are used simply to operate the active fire precautions in the building, such as this automatic opening vent that we can see here. Now, while we were at the top of the stairs, there was a separate roof hatch, and we were given access through the roof hatch onto the roof. And that's what these pictures are. The left-hand picture is showing us here. Now, separate from the automatic opening vent, the building's provided with a smoke extraction system via that shaft that we saw on the earlier plans. On the roof, that shaft leads up to this extraction equipment, which includes scrubbers and various things for the smoke. And these two pieces of equipment that you can see my hand holding part of in this picture should be connected by a rubber grommet that connects the two. As it happens, the rubber grommet was entirely disintegrated, and the circlip there that I'm holding that should have held it in place was loose and falling away from the machinery. Now, that will mean that the smoke is not removed with the same velocity as it would be designed for, because it's designed to be taken out through this machinery and extracted and dissipated into atmosphere from the building. So that is not going to work as it should. Now, the picture on the left is a picture of the corridor extraction system. You can just about make out on that picture that it says smoke shaft door. So this is a door to the smoke shaft, and this is what would be powered open again by the L5 smoke detection system, and it would power that door into the open position, which we will see a little later. And as it powers open, the fans would ramp up, and this mechanism is designed to take the smoke from the corridor and discharge it off the roof.
Okay, so as we stated before, we've got a firefighting stairs. We do have a firefighting lift. What the regulations require us to have would be a 120-minute non-combustible shell, basically. In this case, it's a concrete shaft. Even though it's a steel frame structure with concrete floors, normally the firefighting stairs is one of the first elements to get built first. We do expect certain bits to be in this staircase, such as emergency lighting. As spoke about, you need an AOV at the head of the stairs, and also fire exit signage. And then we also need to look at what type of doors are on each landing level. In this case, we have firefighting stairs and technically a firefighting lobby. However, if we look a bit more closely, we do have service risers containing gas in that firefighting lobby. Normally you expect an FD60 door at each landing level. If there wasn't any gas in that surface riser and you have a lobby, you could argue 230 FD30 fire doors would be sufficient, but we do have an ignition source now in the firefighting lobby. So when we talk about gas, you also need to look at other regulations, such as gas use and installation regulations. That will determine how service risers should be vented, which Richard will talk about a bit later on. So we do have an adequate firefighting stairs. The stairs has to have a certain width. That's due to fire personnel and potentially getting access to fire, and also potentially two-way access of any other residents escaping. So the overall width will be a minimum of 1.2 meters.
At the top or the head of the staircase and at the bottom of the staircase, we found evidence that the Waking Watch personnel were making themselves comfortable. They had introduced, in particular, this swivel chair. They were plugging in electronic devices, reading papers. I think there's a crossword or similar on that stool that they've introduced there. So we have live electricity, we have combustible materials, and we have the chair poses an obstruction risk to anybody who's trying to use the staircase as their means of escape. Especially since it's on casters, it's likely to move around that lobby area and could cause a real problem for people escaping the building. Now, it's interesting in itself that the Waking Watch would make themselves comfortable in what is a means of escape route and potentially a place of relative safety when the fires are likely to happen in flats, and our risk in this building is that the fire could escape from a flat and get into the external envelope of the building and burn all around the outside. So it might be better for these Waking Watch to be spending some of their time outside the building looking for signs of fires on the external facade and walking the corridors rather than making themselves overly comfortable in the staircase enclosure. They were at least provided with an air horn, which you can see in this photograph here, which would enable them at least to make an effort at raising an alarm on the residential corridors. But this is not the best way for them to go about doing their job. As we come out of the staircase onto the residential corridor, we measured the length of the corridor. It seemed too long. Now, typically, according to regulations, the furthest distance that we should have to travel is 7.5 meters from the furthest door to the staircase enclosure. And in this case, our tape measure was well over 15 meters. Now, this can be achieved by using smoke control systems and showing that the extra distance is no worse than the standards proposed in approved document B. But we'll talk more about that in a moment. While we were in this corridor, there was a ceiling hatch in that ceiling there, and we investigated. We opened up the hatch and we could see that within the ceiling there were services running, including the gas and electric. There were fire system cables. So all the usual things that we might expect to see passing through the ceiling and then being routed into each flat. We did not see evidence for those light fittings being protected on the top face of them. So where all the heat can collect in the ceiling cavity, we did not see any evidence of those being properly fire protected. Although we didn't make a full check of these throughout the building, we only carried out a sample. So by no means any kind of comprehensive review of ceiling voids. Now you can see, oh, sorry, go back one. Yeah, back on this floor plate. There were some smoke detectors in there, and we were able, with that view through the hatch, to get a fairly good view of the walls above the ceiling, and we were quite content with the way in which those walls had been finished so that fire from a flat could not get into the corridor, or likewise a corridor could not get into the flat. In the distance there, you can see a figure. That's Paul standing at the end of the corridor, and behind him is the smoke extraction point, and the person taking the photograph is standing just in front of the lift lobby. Now, while we're on this floor, we couldn't find any inlet air. So I spoke earlier about the ability of that smoke shaft to extract air from this corridor and the potential of creating a vacuum. Now, typically, inlet air would balance that system so that as air is extracted, fresh air is coming in. And in this case, we couldn't find anywhere that the fresh air would come in. Now, typically that would be through, in other cases, maybe an openable or automatically opening window, or perhaps through another, an inlet air shaft, which would open at the same time as the smoke extraction shaft. And in some cases, the makeup air is provided from the staircase AOV, and the doors are hung the other way against the means of escape, so that air from the AOV can travel down the staircase enclosure and be drawn through the door, and those systems tend to pull the doors open a little bit to provide fresh air onto the corridors. Now, without that inlet air, there is the risk of creating a vacuum in this corridor, which can make the doors hard to open. As the air is being sucked out, doors can become difficult to pull open, and if that gets beyond 100 newtons in terms of the power required to pull the door open, that is beyond what we can tolerate, because most people would not be able to open it. So this is a particular concern for us so far on this inspection. Now, as we're moving around the building, we get to see all of the fire doors, and we've got a number of inputs here on the door. In the left-hand picture, what we can see is that a door here has at one point had a locking device fitted in it. Now, as it turns out, the lock had been removed, but the mechanism was still present. You can see it was a deadlock of some form, and that it creates a hole that passes all the way through the door. So there's no way that we could classify that as a fire resisting door, insofar as smoke and fire would find that hole as a weak point and would pass straight through the door with no real difficulty. On the right hand picture, we can see a vision panel provided to the doors, which is very useful. You can see if somebody is on the other side of it, or more importantly, if fire and smoke is the other side of the door. So it helps you to make decisions in terms of your evacuation. The glass in the door is Georgian wired glass, and it's normally held in place by a particular beading system, which is appropriate for holding vision panels into fire doors. And in this case, what we have is a kind of semi-sticky mastic that we were able to touch, and it stuck to our gloves. And in any case, it wasn't complete around the glass. You can see that it doesn't meet up, and there's a gap here, and that would be a gap that fire and smoke would attack, and it would in itself weaken the door, and it would not last the designed period of fire resistance there.
Okay, so we as we go around the building, we open up as many service shaft doors as we can to get a good idea of what is inside them. So what we have here is the main service riser shaft, and it's open, so it's not sealed at the floor and ceiling, which is what you quite often find in most buildings these days. So what this allows the building to do is pass the hot water pipes and the gas pipes up and down the building. So if you've got a gas pipe, it does need to have some form of ventilation throughout the building. We looked upwards here, and it was there was no ventilation at all. So so that's obviously something that we need to consider as being a bit of a problem in this building, because gas is lighter than air. It should be able to rise up through these shafts and go out of the ventilation at the top of the building. This wasn't possible here, so this is obviously something that could allow the buildup of gas within the building, which could be an explosive atmosphere. So that's something to consider under the fire risk, but it may also be accessible under the hazard of explosions. So it may be worth considering under that also. Okay, so moving on to also within the same cupboard, we saw some in the cupboard next door. There was some. So what we have here is electricity cables, the black ones, some comms cables, which are the white ones, and some fire alarm cables. And they had passed through what appeared to have been fire stopped originally, what we can see here is some fire stopping. And obviously it appears that some alarm engineers have cut through this to pass the additional alarm system cables through, and they haven't resealed it afterwards. So this was present in one of the cupboards, and if you find one problem, you normally see it in all of the cupboards. However, in this building, it was particular just to one of the cupboards. So and we noted where it went, and it was passing between the lift lobby and the and the service shaft. So any fire in the service shaft would compromise just the one lift lobby on the top floor. So that's something that we need to make note of for our HHSRS inspection. Over to John.
I said that we would look at doors again, and here you can see where we've taken pictures of the top edge of the door leaf when we've opened it. And on the left-hand side, you can see that there's a BM Trada door scheme fire plug. And that tells us that that door is a 60-minute fire door. So what we've got there is a blue plug with a red tree in the center of it. The blue plug represents that it's a 60-minute door, and the red tree says to us that the intumescent material with which the door should be provided has not been fitted in the factory. So the intumescent strips, smoke stop seals, have been fitted as a retrospective upgrade. In the right-hand picture, we've got a certificated fire door. It's marked with that label on the top edge of the door, and that tells us that it's a fire door and that it lasts for 30 minutes. Now, that door in particular was on the lift lobby, and as a part of the fire protection to the staircase, which should have been provided with 120 minutes of fire protection. And they are not going to get 120 minutes of fire protection with a 30-minute door. So this was being used in combination with a 60-minute door. So that would get them up to 90, but not up to the full 120, which they should have had. Now, this slide is showing the smoke shaft door opening. It's on this automatic actuator, and as it's opening, while we were there, we could hear the operation of the fans ramping up, but the draw in the staircase was nowhere near as strong as we might have expected or that we've experienced elsewhere. And we're confident at this point on the floor plate that the lack of suction we're feeling is a result of that grommet missing on the roof. And so we're not getting the volumetric movement of smoke through the corridor, of air through the corridor, sorry, that we would expect. So that system is really not working as it should have been. Now, this was operated for us by the building management, but ordinarily would be activated by smoke detectors.
Okay, right. So we're going into sort of the internal of the flats now. So we've done the communal inspections. We looked outside. You hopefully will get access to a percentage of the flats in the building. What we look out for as we just enter a flat, obviously we've worked out there should be an FD30S fire door entering the flats, and the S stands for smoke seal. As you can see from our inspection, missing cold smoke stop seal along the perimeter of the door, or they could be attached to the door frame. What we also expect from a flat entrance door is a self-closure. That's also missing, and the reason why a front entrance door needs to have a self-closure is because as you exit the flat in an evacuation of a fire, the door should close to contain that fire as much as possible until personnel come to extinguish the fire. As you do inspections, you will see a number of issues with the front entrance doors. They're never perfect. In this case, we've got now sort of on the outside of the door, so in the communal corridor area, as you look at the door, there's been added papers to that door. So for a fire door to be given the classification of an FD30 or an FD30S, it needs to go through a test. That includes any door furniture need to be part of that test as well. That could be, you could be doing a site inspection and the locking mechanisms gets changed, or the handles gets changed, or additional alterations happen to that door. It then technically fails that test an original purpose of that door, what was tested for. So when you do get added flammable material added to that door, that does add to the declassification of that door potentially. Richard, would this be a management issue?
Yeah, so this is something that you may address with the manager of the building, or the owner of the flat, indeed, if they were around and willing to talk to you. But it's not necessarily something that you would take into account in terms of your HHSRS assessment, because they're not permanent adornments to the building. They're temporary sort of attachments to it. So it's not something that you'd necessarily take into account as part of your HHSRS assessment.
Okay, thank you. So as you're inside the flats, you'll be looking around. What certain elements you'd be looking at would be the smoke detection. There's two types normally we commonly see. LD3 systems where there's a smoke detection and sounder incorporated in the internal corridor, or it could be an LD2 system where smoke detectors are provided to other rooms, such as the bedrooms, lounge, heat detector in the kitchen. And then you also get other penetrations to that flat. So when there was an internal fire, that's a source where anything like a room vent, in this case, a lot of flats have recyclable air changes ventilation system. We normally get an outside vent to push the air out, and an internal vent to draw the air in. And these go through the cladding system, and these are penetrations that need to be very careful of. A lot of flats have them. It's very rarely we go to a flat that doesn't have this type of system anymore. And then you got on the internal doors and the front doors, there's a cold, not a smoke seal to the front door. It seems to be a draft excluder. So you need to see what type of smoke seals are to the front door, and if they've been added, anything's been added on there, such as draft excluders. In this case, we were very suspicious of the smoke seal around this door, it was deemed to be more of a draft excluder of some sort.
We've also got, as we look on the inside of the door, an excessive gap over 4 millimeters between the leaf of the door and the edge of the frame. So we've noticed this on the flat that we've inspected here. So this might need more investigation, looking at if this is a common problem across a number of different flats. So you might want to have a look at a few more flats if you notice there to be a problem with the fire doors such as this.
Okay, so as you get access into the flat, you also then be able to access the balcony. This is where potentially you could get more in-depth feel and look at the cladding system as well. You could look around the edges, underneath sills, use a borescope to get a bit more in-depth knowledge of exactly what you're dealing with. So all the flats have a balcony adjacent to the ACM on floors 1 to 7 and HPL wall system on the 8th floor. On this balcony, we do have a composite decking, that's Euro Class D. As we've gone through the Euro Class classification earlier on, you'll be able to see where Class D fits in that. So there's a composite floorboard, but that's a resin board with some timber fibres technically glued together, which makes it a Euro Class D. You could get normal decking board. That would be slightly worse, but you could also get some sort of fire performance to be added to that to bring that Euro class up a little bit further as well. But when you're doing the balcony inspections, you need to basically also look at what's ignition sources are there. There could be a balcony, there could be a lot of, there could be a barbecue, there could be other storage left on that balcony. That if that did that's right adjacent to the cladding system, and then there is a potential for ignition source for that cladding system to capture light. And also just be wary that these balconies are in series. So if you did have a balcony fire at one level, it would also reach the balcony above. So fire can bypass any sort of fire stopping and also penetrate the flat above if the fire stopping and cavity barriers aren't adequately installed, or actually being installed there during the construction stage.
So in terms of the HHSRS assessment of balconies, it's not always just the presence of a barbecue and shisha pipe on the balcony, it's the potential for them to be there. So on a balcony such as this, you've got a fair amount of depth to it, which would permit a balcony or shisha pipe to be positioned on it. We do quite often find them on balconies where people are enjoying the outside space. So it's the potential for them to be there, not just the presence of them. Okay.
So as you're doing your external evaluation on the balconies, you may also see other penetrations or ignition sources. In this case, you can see there's a light been added to the cladding system. So you got wiring, you potentially could get an electrical wire fire. And you also have a waterproof plug socket. That generally have an IP rating. However, you can plug anything into that onto the balcony. Could be lights, and if lights are surrounding the balustrade or around any glass balustrade or around the door frame, that's also an ignition source. And you also do have then holes behind these elements going through the cladding system as well. So it's not ideal. So as you're looking at the external cladding system, you can get a bit closer to it. In this case, we can now, if you access a balcony to the crown of the building, that's the top half of the building where the HPL has been installed. You can visibly touch, feel and measure the cladding, in this case the HPL, and it's normally around about 12mm thick at the edges. It's slightly different from ACM. It does have a different sort of texture, thickness. And if you do see an external edge, the appearance of the edge should be different as well. And as we know, the HPL is Euro Class D S2 D0. So you need to be careful of any ignition sources. One thing to be wary of is also the building regulations, which states back at the time the cladding system should have had a Euro Class B or better with an installation Euro Class A or sort of A1 to A2. So in this case, we do have a failing cladding system to the crown of the building that technically may or may not have complied with the building regulations. But you need to also have a look at the fire strategy, any justifications for that as well.
Okay, what we have here is our reception. The escape route taking us from the top of the stairs comes down the stairs and then vacates, empties and discharges out into this area here, where we have a reception desk with a small office behind it. We also have post boxes here, which are likely to contain paper. And also within the office, we have a look around inside there, and we note that there's a fair amount of daisy chaining in there, which is the connection of electrical appliances to extension leads to another extension lead. So that's all very bad practice, and you tend to have overloading of those plug sockets. So that creates a bit of a fire risk within there. You'll also note that there's a door here that's not self-closing, and it's also not a fire door. So any fire in there is likely to come out of there pretty quickly, which would, considering we've only got one escape route from the residential areas, be quite a serious problem and will compromise the entire escape route. So that's something that is likely to be very important in your relevant matters.
These two pictures show us the final exit doors, respectively, on the left-hand side from the car park, and on the right-hand side, the main entrance security door to the reception area that we just saw. From the car park here, starting with the picture on the left, this door has been fitted with a push bar to open, which is typically associated with large numbers of people and crowds, and the ability to crash out of the door by just pushing up against it. It's perfectly fine for the car park situation, but it's also been fitted with this other device here, which is labelled as a Redland bolt. It's got a small hammer on a chain, and that is used to break a glass tube that holds a spring-loaded release device locked into the door frame. So if you were to break the glass, the spring would push back against that lock and it would unlock. Now, in themselves, no particular problem, but an exit door should only have one means for opening it. It should not be fitted with two escape mechanisms. It means I've got to go through two separate actions in order to open the door, and I should only have to go through one single action to get out of a fire escape door. Now, on the right-hand picture there, you can see that there's the fob access and that the door is a pull door from the outside, which means that it's opening in the direction of escape from a fire inside the building. And this was in itself quite a good door. There were no particular issues with it. So from the ground floor, we descended into the basement car park, and the left-hand picture here shows you some soil pipes, and they've been surrounded with this expanding pink foam. It's lousy stuff. The pink foam is not in itself a terrible thing. It is designed to go between two solid objects, like two pieces of concrete or a stone wall and a solid concrete. Now, what's going to happen if there's a severe fire in the car park is that these plastic pipes are going to soften and melt. And as they do that, they will create a hole through that concrete floor and therefore a mechanism for fire and smoke to pass through the floor and into the ground floor areas. So this is not a good solution. The foam is not going to do anything other than fill the gap around the pipe and the concrete floor there. So what they should have is an intumescent collar around them, which can be fitted into the concrete floor itself, so that as it expands, it pushes against the concrete floor, and then as the pipe melts and softens, that expansion pushes into the pipe, crushes the pipe, and forms a complete seal. Other types are external to that, and they're fitted in a steel cage. The steel cage is attached to the concrete floor, and that contains the intumescent material. And again, as the pipe softens and melts, the intumescent expands, in this case against the steel cage, and fills the gap. But neither of those two products were here. We had this awful expanding pink foam instead. And that wasn't the only place we saw expanding pink foam. You can also see it to the right-hand side of the light and where these pipes are passing through in the right-hand picture. So again, you can see the pink foam where it's been cut off in this case. And this is in quite a large rectangular shaped hole that was passing through the building. And if there were a fire this side of the wall, that pink foam would more likely contribute to the fire than it would protect anything from it. So that hole should be filled with firebat or with intumescent pads or pillows or some other form of passive fire protection that's going to stop fire passing from one side of that wall to the other.
Right, so good place to be. So you've looked at the external of the building, you've looked at the internal service risers, firefighting stairs, communal corridors, you've gone into flats, you've worked your way down to the car park and basement to the final sort of ending of your inspection. So in the basement, you normally do get a plant room or a number of plant rooms as well. They contain other services, pumps, etc. And in this case, we found a riser hidden going up through near enough the central part of the tower, where the floor is where it's going through the ceiling of the slabs, the ceiling slab. Don't forget these are concrete floors, and you can see light at the top. So this is basically an open flue going from the basement plant room right up to looks like to the roof. As you can see, daylight. The floor to the basement you expect to be at 90 minutes fire resistance. So you need to look at what fire resistance of the structure should be built to, what part of the building regulations. In this case, it's 90 minutes to the basement floor, and it's not sealed. So if there was a fire in the plant room, then it could spread up through the central part of the tower to each flat. Added to that, also the construction of that shaft itself should be questioned, because it should have 60 minutes fire resistance around the sides of that as well. So if a fire did break out, it won't penetrate into each flat, and that floor should also be sealed for 90 minutes. If it was a fire rated flue going up through there, you wouldn't be too worried. But you also need to check what that type of flue that is. But as you can see in this riser, you can see a number of services going up there as well, and it's not fire stopped or has any protection at the plant room level.
Yeah, if you remember, Paul, it wasn't daylight shining down from there. I popped up to the second floor and shone a torch down it, and you were able to see that light coming down from even just the second floor. So it was passing through from the basement to the ground to the first at least. So we still had a big problem there of potential for fire to go from the plant room and spread its way across the floor plates of the building above.
Precisely.
Okay, also within the outside of the building, we got access to the bin store. What you will see here is a number of normal sort of refuse bins that we would see in there. But we've also noted that there's a fair amount of pallets that have been stored, which could sort of collapse at any time realistically. But most importantly, the fire loading within there would be quite considerable. So if say, for example, someone disposed of a cigarette or something, caught on the leads at the bottom of here and set fire to this, we could have quite a serious fire incident within the building itself. You'll also see where some of these have fallen against the break glass point, which is part of the L5 system. So obviously that's not a good thing. That now won't work. So any fire within the bin store won't be able to be reported. They'll have to get back into the building via the front entrance to get to another break glass point to sound the alarm. However, in terms of your HHSRS assessment, this is a behavioural rather than a feature of the actual of the building itself. What you're really looking for in terms of the bin store is there actually adequate bin space for the number of people that are in the building? What might be indicative that there isn't is that you've got a number of overflowing bins, for example. That's not the case in this one, so that we will take that into account in our relevant matters. However, obviously we've got some damage to the alarm system there, so that is obviously relevant.
Just on the call point there, Richard, it's possible that call point would still raise an alarm. In fire safety terms, we would want that to be well maintained, and there's a 3-part test in the fire safety order for being maintained, and that's that the thing is in an efficient state, in efficient working order, and in good repair. So this one is definitely not in good repair, because that should be screwed into the wall and it should be level and it should be fitted correctly, and it's certainly not meeting that part of the standard. But it might well be in working order still. The glass looks intact. I can't remember what was above that and whether the wiring had been affected, and maybe your memory is better than mine. But it's possible it was
purely just the front plate had been detached.
Yeah, in which case it might be in working order, but it's not in good repair. And so there'd still be some work to do, certainly under the fire safety order, with respect to that device in particular.
Yeah, that's great stuff. Thanks, John. Okay, so other issues, having reviewed your relevant matters which are present in the addendum to the hazard of fire, it's worth noting that there were no other obstructions noted on the escape route and stair, and that it was of a satisfactory width, as John said, or as Paul said earlier, at 1.2 metres. So that's not an issue here. So we wouldn't be scoring that. So there was no sprinkler protection to the building. The building is below 30 metres, which is the level at which sprinklers are routinely required now to a building. Or alternatively, sometimes you find they are in smaller, shorter buildings where there is an issue with open plan flats, for example. But that's not the case in this instance. There's emergency lighting to the, as we saw on the escape route, that was okay and had been certified as part of the documentation that we went through at the start. The signage, which was adequate to the building, it's a relatively simple escape route, and that was deemed to be adequate within the building. The lightning protection was provided. That had been certified and was okay and in reasonable condition, which we could see from the top of the building around the ring of the top of the building. The dry rises are tested regularly and we have been provided with certificates. Test certificates have also been provided for the AFD, so the fire alarm system, and the electrical installations for the firefighting lift, which is different to a LOLA certificate. The firefighting lift actually needs a separate inspection to what many people interpret as being a lift test certificate. So it's an actual firefighting lift test certificate. And there was also a certification for the smoke control system. We suspected that they perhaps haven't properly undertaken this assessment, but they have provided us with a certificate. So we will question that probably with them at a later date. And obviously, as John said earlier, there was 100% access to the outside of the building, so firefighter access was indeed adequate. Okay, so that brings an end to the day's inspection. We tend to get together as a team and discuss what we've found. So now is the time that we would like you to undertake scoring of the relevant matters and to undertake your own HHSRS score. You will find in the addendum, which we will attach a link to as with the email that has come. The relevant matters are all in there, and we will provide to you an Excel spreadsheet to assist you to score them also. So feel free to use that. That will automatically tot up the scores, and you'll be able to compare it against the scores that are in the worked example, which has been provided. For the training day to be successful, please keep a note of your scores and have them handy, as we're going to be doing some live polling on the actual Teams meeting, and have a think about where your score compares against the addendum's worked example. So have a think about that and have a compare of it. Okay, so that's the end of today's training session, and I look forward to meeting you in person on the training day. Thanks very much.